Dear students, welcome to the second part of Module 2 of the course Solid State Devices. Myself, Assistant Professor JasminSebastin from the Department of Electronics and Communication Engineering, RSET. Part 2 of Module 2 would be covered in two sections, of which this is the first section. In this section, we will discuss about the variation of mobility with temperature and doping. Also, we will discuss about two phenomena called the high field effect and the Hall effect. So, let's start the session. In part 1 of Module 2, we discussed about drift, conductivity and mobility of charge carriers. Now, let us see the dependence of mobility on temperature and doping. There are basically two types of scattering mechanisms that affect the mobility of charge carriers in a crystal lattice. The scattering mechanisms are lattice scattering and impurity scattering. Now let us see what is lattice scattering. At very high temperatures, the crystal lattice is thermally agitated. Therefore, a carrier moving through the crystal is scattered by a vibration of this lattice. This is called lattice scattering. At high temperatures, the frequency of lattice scattering increases. As the frequency of scattering increases, the mean time between scattering decreases. In the previous session of Module 2, we saw that mobility of charge carriers is directly proportional to the mean time between scattering. Therefore, at high temperature, the mobility decreases. This temperature dependence of mobility due to lattice scattering is given by T raised to minus 3 by 2. Lattice scattering is also called phonon scattering, as the collective vibration of atoms in a crystal lattice is also called phonons. So that is about lattice scattering, and lattice scattering is prominent at high temperatures. Now let us see what is impurity scattering. As the name indicates, impurity scattering is caused by scattering from crystal defects such as ionized impurities. This type of scattering is prominent at lower temperatures. So what happens at low temperature? At low temperature, the thermal motion of carriers is also slow. Therefore, they have a tendency to be strongly scattered by ionized impurities. So what happens? Impurity scattering leads to decrease in mobility with decrease in temperature, and this temperature dependence of mobility due to impurity scattering is given by T raised to 3 by 2. So, impurity scattering is the type of scattering that is prominent at lower temperatures, and lattice scattering is the type of scattering that is prominent at higher temperatures. Let us look at this graph. This graph shows the variation of mobility with temperature. Mobility is plotted along the y-axis and temperature is plotted along the x-axis, both on log scale. We can see that impurity scattering is dominant at lower temperatures and mobility increases with increase in temperature. The dependence of mobility due to impurity scattering on temperature is given by T raised to 3 by 2. And lattice scattering is seen to be dominant at higher temperatures, and we can see that the mobility decreases with increase in temperature, and the dependence of mobility on temperature is given by T raised to minus 3 by 2. In the previous session of Module 2, we learned that the scattering probability is inversely proportional to mean free time and therefore inversely proportional to mobility. The equation showing that relationship is given as dpx is equal to minus px into dt by t bar. This equation was explained in session 1 of module 2. And the equation for mobility mu n is equal to qt bar by mn star. Since scattering probability is inversely proportional to mean free time and therefore inversely proportional to mobility, if there are two or more scattering mechanisms that contribute to mobility, the mobility due to these mechanisms add inversely. Or we can write the total mobility 1 by mu is equal to 1 by mu1 plus 1 by mu2. From this equation, it can be easily understood that the mechanism which causes the lowest mobility value dominates the mobility. Now, we discussed the effect of temperature on mobility. The effect of doping on mobility is found as the concentration of impurities increases, the effect of impurity scattering starts getting felt at higher temperatures. That is the effect of doping on mobility of charge carriers. So with that, we have come to an end of our discussion of variation of mobility with changes in temperature and doping. Now let's discuss about a phenomenon called high field effect. In the previous session, we assumed that the drift current is proportional to electric field and the proportionality constant is given by sigma. So this equation is written as Jx is equal to sigma into epsilon x, where Jx is the drift current and epsilon x is the electric field and sigma is the proportionality constant. This proportionality constant sigma is not a function of the electric field epsilon. We also know that J is equal to minus Qn into Vd, where Vd is the drift velocity of carriers. At very large electric fields of the order of greater than 10 raised to 3 volt per centimeter, it was found that the drift velocity Vd does not exhibit a linear dependence on electric field. That is, it has got a sublinear dependence on electric field. Because of this, the current Jx also exhibits a sublinear dependence on the electric field. This sublinear dependence of sigma upon the electric field epsilon is an example of a hot carrier effect. Now, what is hot carrier effect? When the carrier drift velocity Vd becomes comparable to the thermal velocity Vth, that is called the hot carrier effect. The relationship between drift velocity of charge carriers and the electric field is shown in this plot. The drift velocity is plotted along the y-axis and electric field is plotted along the x-axis. Till a particular point, the relationship is found to be linear. An upper limit is reached at the thermal velocity of about 10 raised to 7 centimeter per second. After this point, we can see that the drift velocity does not increase, it remains a constant. So it means that instead of increasing the drift velocity, the energy from the electric field is transferred to the lattice. That is, the velocity is limited and the energy is transferred to the lattice. And this causes a nearly high constant current at very high electric fields. This is called high field effect. So now we have completed our discussion about the effect of temperature and doping on mobility. Also, we discussed high field effect. As the name indicates, at very high electric fields, the drift velocity of charge carriers ceases to increase after a point and it remains a constant. So whatever is the scattering limited velocity causes a very high current at high electric field. This is called high field effect. Now let us come to the final topic of discussion of this session, which is the Hall effect. What is Hall effect? It can be explained as when an electric field and a magnetic field are applied simultaneously in mutually perpendicular directions to a semiconductor material, another electric field develops in a direction which is mutually perpendicular to both the applied electric and magnetic fields. That is called Hall effect. Here let us consider this semiconductor crystal shown in the figure. It has got a dimension of LWT, where L is the length, W is the width, and T is the thickness of the semiconductor material. An electric field epsilon x is applied in the x direction. So here we are considering the movement of holes. So we know that holes move in the direction of electric field. A magnetic field BZ is applied in a direction perpendicular to the direction of epsilon x or the direction of hole drift. Let Ix be the current along the x direction due to the applied electric field epsilon x. So what happens is, now we have an electric field epsilon x applied along the x direction and a perpendicular field, magnetic field BZ, applied along the z direction. So when a magnetic field BZ is applied, the path of the holes tend to deflect. Now the holes move in the direction of the applied electric field epsilon x. When BZ is applied in a direction perpendicular to epsilon x, these holes will experience a force and they will tend to deflect. The force experienced by the hole due to this magnetic field BZ is given by Q into Vx into BZ. Q into Vx into BZ, and that is in the negative y direction. That is, there is an electric field epsilon x applied in the x direction and the holes are drifting in that direction. Now we applied a magnetic field BZ in a direction perpendicular to epsilon x. Due to the magnetic field, the holes experience a force Q into Vx into BZ. That force is in the negative y direction. So we can write the force due to the applied magnetic field BZ is minus Q into Vx into BZ. And the holes tend to deflect from their normal path of motion. Now to maintain a steady state flow of holes down the length of the bar, an electric field epsilon y must just balance the force due to magnetic field, that is Vx into Bz. So if an electric field is developed epsilon y in y direction, the total force on holes would be given by this equation. Fy is equal to Q into epsilon y minus Vx into Bz. Why is there a minus sign? Because epsilon y is in the positive y direction and Vx into Bz, the force due to magnetic field, is in the negative y direction. So this epsilon y should be developed in order to maintain a steady state flow of holes down the length of the semiconductor bar, and that epsilon y and the force on the holes due to the magnetic field are in opposite directions. So the net force on y direction Fy is equal to Q into epsilon y minus Vx into Bz. When this epsilon y just balances Vx into Bz, the net force along the y direction becomes equal to 0. So there is no lateral force experienced by the holes as they drift along the bar. So when is epsilon y set up? Epsilon y is set up as the magnetic field starts shifting the path of the holes, and once epsilon y is set up, the holes do not experience a net force in the y direction because this epsilon y exactly balances the force on the holes due to magnetic field. So this setting up of epsilon y is called Hall effect, and the resulting voltage, that is epsilon y into the thickness of the width of the semiconductor material, W, is called the hole voltage. So how do we explain Hall effect? Let us see the semiconductor material once again. An electric field epsilon x is applied in the positive x direction and the holes move in that direction. So now we apply a magnetic field Bz in a direction perpendicular to epsilon x. Because of the application of this magnetic field, the holes experience a force Vx into Bz in the negative y direction. Because of this force, the path of the holes tend to deflect. Now, if the path of the holes must not deflect, and in order to maintain a steady state flow of holes, an electric field epsilon y, which just balances the force on the holes due to magnetic field, is set up along the positive y direction. That is, epsilon y, q into epsilon y is equal to q into Vx into Bz. So, the net force along the y direction becomes 0 and the holes can drift along the bar with no net lateral force in the y direction. So, this setting up or establishment of an electric field epsilon y is called the Hall effect, and the resulting voltage is called the Hall voltage. Now let's see some important derivations. From the previous session of module 2, we know that Jx is equal to minus Qn into Vx, and we know that epsilon y is equal to Vx into Bz. So now let us substitute Vx. Vx is equal to Jx minus Qn. Since we are considering holes here, minus q changes to plus q and n changes to po. So instead of Vx, we are substituting Jx by q po, and epsilon y is given by Vx into Bz. So that is Jx by q po into Bz. So this 1 by q po can be written as RH. So the entire equation for epsilon y can be written as RH into Jx into Bz, where RH is equal to 1 by q into po. That is, the Hall field epsilon y is proportional to the product of current density Jx and the magnetic flux density Bz, and that proportionality constant RH is called the Hall coefficient. This is one derivation. Epsilon y, the Hall field epsilon y, is directly proportional to the product of current density and the magnetic flux density. The proportionality constant, which is called the Hall constant, is equal to 1 by QPO. Now, we know that PO is equal to 1 by QRH, and that is equal to, what is RH? RH is equal to epsilon y by Jx into Bz from this equation. So 1 by QRH is equal to Jx into Bz by Q epsilon y. What is Jx? Jx is the current density, that is current divided by area. From the semiconductor material, we know that the area, cross-sectional area, is given by the width of the semiconductor material into its thickness. So Jx is given by Ix divided by Wt into Bz, and epsilon y is equal to the voltage divided by length. Epsilon y is the field along the y-axis. Along the y-axis, the voltage is given as VAB and the length is W. So, this can be written as epsilon y can be written as VAB by W. On simplification, this can be written as, that is, the whole concentration PO is equal to Ix into Bz divided by Qt into VAB. So all these quantities are measurable. So if we know the Hall effect, it can be used to find out the carrier concentration. PO is equal to Ix into Bz by Qt into VAB. We know that resistance R is equal to rho into L by A. So what is the resistivity? Rho. Rho is equal to R into A by L. The semiconductor specimen that we considered had a dimension length equal to L and width equal to W and thickness equal to T. So R into A, cross sectional area, becomes WT divided by L. And what is R? Resistance is equal to voltage divided by current, that is VCD divided by IX divided by, we have brought this WT to the denominator, divided by L by WT. So the resistivity can be found out from this formula, VCD by IX divided by L by WT. Next, from the session 1 of module 2, we know that conductivity sigma is equal to Q into PO into mu P, where mu P is the mobility of holes. So mu P can be written as sigma by QPO, and we know that PO depends on the hole coefficient, and that is equal to 1 by QRH. So mu P equal to sigma by QPO. Sigma is what? Conductivity is 1 by resistivity, 1 by rho divided by Q divided by 1 by QRH, that is PO. So on simplification we get mu P, that is the mobility of holes, is equal to RH, that is the hole coefficient, divided by resistivity. So if we know the hole coefficient and resistivity, the mobility of holes is simply the ratio of hole coefficient and resistivity. Now in this particular derivation and explanation of Hall effect, we have considered holes as charge carriers. So if we consider electrons, wherever we used Q, the negative value of Q would be used. Therefore the hole voltage VAB and the hole coefficient RH will become negative. So that means that if we can find out the hole voltage VAB and RH from the sign of the hole voltage, we can determine whether the semiconductor material under consideration is P type or N type. That is an important conclusion. So in this part of module 2, we have discussed about the dependence of mobility on temperature and doping. We discussed about high field effect and Hall effect. We derived some relations with respect to Hall effect, how we can calculate the mobility if we know the hole coefficient and resistance, how we can determine the type of the semiconductor sample if from the sign polarity of the hole voltage, etc. Thank you.